Hello, wonderful people! Here we are, still in chapter 37, electromagnetic induction. Today we're going to cover transformers. This is section 5, so here we go. A transformer works by inducing a changing magnetic field in one coil, which induces an alternating current in a nearby second coil. So we definitely need pictures. We've got a pair of coils side by side, one connected to a battery and one connected to a galvanometer, which measures current. It's customary to refer to the coil connected to the power source as the primary and the other one as the secondary. So the primary coil is the input and the secondary coil is the output. As soon as the switches close in the primary and current passes through its coil, a current occurs in the secondary. When the primary switch is opened, a surge of a current again registers in the secondary, but in the opposite direction. Whenever the primary switch is opened or closed, voltage is induced in the secondary circuit. The magnetic field that builds up around the primary extends into the secondary coil. Changes in the magnetic field of the primary are sensed by the nearby secondary. These changes of magnetic field intensity at the secondary induce voltage in the secondary in accord with Faraday's law. So here's what's going on. You shut this, a current flows through this. And as the current starts to flow through this, it builds up a magnetic field. So let's say the north is on this end and the south is on this end. Well, this secondary coil feels that magnetic field as it builds up in the primary. So there's a magnetic field that's going through the secondary and is changing. It's getting bigger as the primary gets bigger. Well, now a moving magnetic field through a coil of wire, that's going to push the charges around. So the magnetic field that's being built up in the primary from the battery extends to the secondary, and this magnetic field now pushes current around in the secondary. Now, once this is shut and this field is all the way built up, if this switch stays shut, then this field gets as big as it's going to get, and then it just stays there. So once the field is done growing in the primary, the secondary catches up to the primary until its field is the same size as the primary. And then the current drops back down to zero. So the only time that current is moving in the secondary is while the magnetic field in the primary is changing. Remember, you need to have the magnetic field crossing the wires in order for there to be a push of the current, of the charges in the wire. And that is the trick to the whole thing right there. So let me repeat it briefly. The primary, you shut the switch, the coil, the current flows through the coil. As the current flows through the coil, a magnetic field builds up. It starts from nothing and then it builds up and up and up until it gets to as big as it's going to get when this stays shut. While that magnetic field is building up in the primary, it's going through the secondary. And that changing magnetic field in the secondary now produces a current that you can measure. Once the primary magnetic field is all the way built up, it will build up all the way in the secondary, and once it's done building up in the secondary, the current drops back down to zero. Okay. As soon as the switch is closed, we did that. Magnetic field that builds up around the primary extends into the secondary coil. Changes in the magnetic field of the primary are sensed by the nearby secondary. These changes of magnetic field intensity at the secondary induce voltage in the secondary in accord with Faraday's law. If we place an iron core inside both coils, alignment of its magnetic domains intensifies the magnetic field within the primary. The magnetic field is concentrated in the core, which extends into the secondary, so the secondary intercepts more field change. So basically, if you add iron into the middle of it, it just makes the magnetic field stronger and more directed directly into the secondary. The galvanometer will show greater surges of current when the switch of the primary is opened or closed. Oh, so I didn't say that the part about, where does it say that? When the primary switch is opened, a surge of current again registers in the secondary in the opposite direction. So let me explain that real quick. So we have this shut. The magnetic field is completely built up in the primary and in the secondary. Then we open this. Well, once we open this, the current stops in here. Now the current stops instantly, but the magnetic field is still there. So now the magnetic field starts to go away. And as the magnetic field in the primary goes from a big field down to a zero field, it shrinks out of the secondary. And once again, the magnetic field that's passing through the secondary back into the primary as it goes away causes a current. Now the difference is the current in the first time, let's just say it went to the right, and now the current the second time as the field is going down goes to the left. So we add the iron to make the magnetic field as strong as it can be. And this is where we make it useful to us in the everyday world. Instead of opening and closing a switch to produce the change of magnetic field, we just use an alternating current to power the primary coil. Then the rate of magnetic field changes in the primary and in the secondary is equal to the frequency of the alternating current. And we call this, now we have a transformer, a device for increasing or decreasing voltage through electromagnetic induction. So how do we change the voltage? Let me show you. All right, so this is how most of the old style transformers were built. You would wrap a coil around a big piece of iron, and then you'd have the secondary coil around the same piece of iron, and you'd rely on the magnetic field going through the iron. And yes, they were usually square like this. If the iron core forms a complete loop guiding all magnetic field lines through the secondary, the transformer is more efficient. All the magnetic field lines within the primary are intercepted by the secondary. And that's what we're going for, increased efficiency. Right. Voltages may be stepped up or stepped down. All right, I'm not going to read this. I think it's easier to show you at this point. So we have one coil. So if we have one coil and we put in 1 volt into this coil, we will get 1 volt out of that coil. Now, if we add a second coil, so we have input coming in here and it's 1 volt. So when this has 1 volt of electricity, this will have 1 volt and that will have 1 volt. So now do you see where we're going? We have 2 outputs and we have 1 input. Well, what happens if we just connect the outputs together? Like that. So now we have 1 volt coming in, and because we have 2 coils going out, instead of 1 volt coming out, now we have 2 volts coming out. So we start with 1 volt, and now we end up with 2 volts. And that is the magic of transformers. This is what allows us to power the whole world. I'll explain how. Oh, and you see how we go up to 2 volts? We can also go down. If we had 10 coils here and 20 here, we would go from 1 volt to 20. But if we had 10 coils here and only 5 here, we would go from 1 volt to half a volt on the output. So you can go either way. And here's how that works. If the secondary coil has fewer turns than the primary coil, the alternating voltage in the secondary will be lower than that in the primary. And we say that this is stepped down. The voltage from the primary is stepped down to the voltage in the secondary. Example, if the secondary has half as many turns as the primary, then only half as much voltage is induced in the secondary. So the phrase step down is what we call transformers in the real world. If the output voltage is lower, we call it a step down transformer. If the output voltage is higher, we call it a step up transformer. And this is how you figure out the relationship. The primary voltage divided by the number of turns in the primary wire equals the secondary voltage divided by the number of secondary turns. So usually you have a given input voltage and you want some output voltage. And then just the way you decide to make it exactly what you want is how many turns of coil you put in there. Now also, the more turns of coil, the more efficient the transformer. So if you had 1 billion coils of wire in the transformer, it would be highly, 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 highly efficient. But 1 billion coils costs a lot of money. Somebody's got to pay for all that copper wire. So there comes a point where you just call it good enough and you say, I'll put 1,000 or 10,000 coils in there. A practical transformer uses many coils. The relative number of turns in the coils determines how much the voltage changes. That's what I said. Now, what is the relationship of power in here? Power is this formula, voltage times current, okay? So you don't get something for nothing with a transformer that steps up the voltage. Energy conservation is always in control. The transformer actually transfers energy from one coil to the other, and the rate at which the energy is transferred is the power. But the power used in the secondary is supplied by the primary. So rather than talking about voltage and current, if I have 100 watts in the primary, voltage times current, 100 watts, can I get more than 100 watts out in the secondary? No. You can make the voltage really high by having a lot of windings in the secondary. But as the voltage goes up, the current goes down. So if I have 100 watts, I could have 10 volts and 10 amps. If I had 100 volts, I would only get 1 amp. If I had 1,000 volts, I would only have 1/10 of an amp. Now, I'm not asking you to figure out all this math, and we're not going to do any math problems using this. All I'm saying is that you need to realize that a transformer puts out whatever you put in terms of power. So you can't use a transformer to magically power up a car, right? You can't put in 100 volts and 10 amps. That would be 1,000 watts, and then light up the whole of North Adams on 1,000 watts. You see what I'm saying there? You only still get 1,000 watts out of whatever you put in, and 1,000 watts is basically enough to power, I don't know, like 1 or 2 houses for a day, just to ballpark it. All right, power. You don't get something for nothing. Power in equals power out. If the secondary has more voltage, it will have less current than the primary. If it has less voltage, it will have more current. This transformer, kind we all plug into the wall, converts 120 volts in the plug down to 6 volts or 9 volts. It also changes it from AC to DC by means of a diode. And that's what those are. There's a transformer in there and a diode, so you get DC out. And what do those usually power? Something like a laptop or phone charger. I'm not going to worry about that. That's a bit much. How does a transformer work? That's what you need to know. How does a transformer work? That describes it. Primary voltage divided by the turns, secondary voltage, number of turns. So there's the number of turns on the secondary. I have another picture showing that. There's another secondary. However many turns and however many turns tells you how much the voltage will change.